Welcome! In this session, we'll tackle LeetCode problem number 551, Student Attendance Record I. This problem tests our ability to analyze strings and apply logical conditions efficiently. We'll explore the key ideas and strategies to solve it. Let's get started. In this problem, we are given a string S that represents a student's attendance record. Each character in the string corresponds to 1 day of attendance and can be one of three values, A, L, or P. A stands for absent, L stands for late, and P stands for present. The goal is to determine if the student is eligible to receive a reward based on their attendance record. For the student to qualify, two conditions must be met. First, the student must not have more than one occurrence of A in their record. Second, the student must not have more than two consecutive L values. If both of these criteria are satisfied, we return true. Otherwise, we return false. This means we need to analyze the string to check for these patterns and determine if the attendance meets the requirements. The output for this problem is a Boolean value, either true or false, depending on whether the student's record satisfies the eligibility criteria. Let's look at an example to clarify this further. For an input string S equals PPALLP, the output would be true. Here's why: the student's record contains one A, which is within the allowable limit of 1. Additionally, there are no more than two consecutive L values in the record. Therefore, this student meets the criteria and is eligible for the reward. Now, let's examine another example. For the input string S equals PPALLL, the output is false. In this case, the student still has only one A, which is acceptable. However, the student has three consecutive L values, and this violates the condition that no more than two consecutive L values are allowed. As a result, the student is not eligible for the reward. Lastly, consider the example where the input is S equals AAP. In this case, the output is false. The reason is that the student's record contains two occurrences of A, which exceeds the allowable limit of 1. Because of this, the student fails to meet the reward criteria. To summarize, the constraints for this problem require that the string S consist only of the characters A, L, and P, with a length between 1 and 10,000. When solving this problem, you should also think about edge cases such as strings with no A or no L, strings that are exactly at the length limit, and records that just barely meet or fail the criteria, like having exactly two consecutive L or exactly one A. To solve LeetCode problem number 551, our goal is to determine if a student's attendance record meets two specific conditions to be considered rewardable. First, the student must not be absent more than once, represented by the character A. Second, the record must not have 3 or more consecutive late days, denoted by L. While the problem is relatively straightforward, we need to ensure that both conditions are handled efficiently. One basic approach we could take is a brute force method. Here, we would iterate through the string and count the occurrences of A, while also checking for any instance of 3 consecutive L characters, such as the substring LLL. This involves two separate checks, counting and scanning for these consecutive L patterns. The implementation is simple: use one loop to count it and another loop or slicing mechanism to check for LLL. While this is a valid solution, it's not the most efficient for longer strings. The brute force approach comes with its drawbacks. In terms of complexity, the time required is O(n squared, since identifying a substring like LLL in the worst case can take O(n), and we may repeat this process multiple times. On the bright side, the space complexity is O(1), because no extra data structures are used. However, the inefficiency of repeatedly checking substrings makes this method less suitable for larger strings. Now, to address these inefficiencies, we can optimize the solution by using a single-pass approach. The key observation here is that both conditions, counting and detecting LLL, can be checked in just one traversal of the string. Instead of searching for substrings repeatedly, we maintain two simple counters, one for the number of A characters and another for consecutive L characters. If we encounter an A, we increment its count, and if the count exceeds 1, we can immediately return false since the condition is violated. Similarly, for L, we count consecutive occurrences and return false if the count reaches 3. Importantly, we reset the L counter to 0 whenever a character other than L is encountered. The implementation of this single-pass approach is straightforward. We initialize two counters, one for tracking absences and another for consecutive late days. As we traverse the string, if we encounter A, we increment the absence counter and immediately check if it exceeds 1. If it does, we return false. For L, we increment a late counter for every consecutive L, and if it reaches 3, we return false. If the character is not L, we reset the late counter to 0. This ensures that we track consecutive late days correctly without unnecessary operations. Once the loop completes, and neither condition is violated, we return true. The complexity here is much better than the brute force approach. The time complexity is O(n), since we traverse the string just once, and the space complexity remains O(1), as we only use a few variables. This method is highly efficient and works well even for larger strings. However, the logic is slightly more complex compared to brute force, which could make it less intuitive for some developers. Still, its efficiency makes it a strong candidate. Another approach to solving this problem is by using regular expressions. With this method, we can handle both conditions, counting occurrences of A and detecting LLL using regex patterns. For example, we can use Python's strcount method to determine if the number of A characters is less than or equal to 1. Simultaneously, we use the research function to check for the presence of the substring LLL. The implementation is concise and leverages Python's built-in libraries, making the code clean and easy to read. However, while this approach is appealing in its simplicity, it comes with its own trade-offs. The time complexity is O(n), as both counting and searching operate linearly, but the space complexity becomes O(n), due to the overhead introduced by regular expressions. Additionally, while regex simplifies the implementation, it may be overkill for such a straightforward problem. The overhead and dependency on external libraries make this method less ideal for competitive programming scenarios. After evaluating all the approaches, we chose the optimized single-pass solution as the most practical strategy for this problem. This method strikes a balance between efficiency, simplicity, and clarity. While the regex approach is concise, it introduces unnecessary overhead, and the brute force method is simply inefficient for larger strings. The single-pass solution takes advantage of the problem's natural structure, ensuring that both conditions are checked simultaneously during one traversal of the string. This makes it highly efficient with minimal complexity. One trade-off is that the logic is slightly more verbose than the regex approach, but it avoids the additional space overhead. Overall, the single-pass solution is robust, performs optimally for large inputs, and avoids reliance on external libraries. For these reasons, it stands out as the best choice for solving this problem effectively. In this problem, we need to determine whether a student's attendance record is rewardable based on two specific conditions. The record is represented as a string containing only the characters A, L, and P, which stand for absent, late, and present, respectively. For the record to be considered rewardable, two criteria must be met. First, the student cannot be absent more than once throughout the record. Second, the student cannot be late for 3 or more consecutive days. These conditions ensure that the student demonstrates a consistent and acceptable attendance pattern. To solve the problem, we start by validating the input. The input must be a non-empty string containing only the characters A, L, and P. If this constraint is not met, it's optional to return false for stricter validation. Once the input is confirmed valid, we initialize a variable called absent_count to keep track of how many times the student has been absent. This is all we need, as the solution doesn't require additional data structures. The next step is to traverse the string character by character in a single pass. As we iterate, we first check if the current character is A. If it is, we increment absent_count. If at any point the count exceeds 1, we immediately return false since the first condition is violated. Additionally, to check for 3 consecutive Ls, we use a sliding window of size 3 during the traversal. If we encounter a substring like LLL, we return false immediately because it violates the second condition. After traversing the entire string, if we haven't returned false, it means the record satisfies both conditions. In this case, we return true. This algorithm is designed to be highly efficient. By processing the string in a single pass, we achieve a time complexity of O(n), where n is the length of the string. The use of early exits ensures that we stop processing as soon as a violation is detected, which avoids unnecessary computations. For the sliding window check, we use simple substring operations like s, I plus 3, to efficiently detect consecutive Ls without additional space. This approach ensures that the solution remains space-efficient, with an auxiliary space complexity of 1. By relying on just a single counter for absences and a straightforward traversal mechanism, the algorithm is both elegant and highly optimized. When considering edge cases, we handle a few scenarios to ensure the algorithm works robustly. For example, an empty string would technically satisfy the conditions since no violations exist, so we return true. A string containing only p, such as PPPP, is also valid. However, cases with a single violation, like AAP where there are more than one A, or LLLPPP which contains 3 consecutive Ls, are invalid. For mixed records like PPALLP, the record is valid as it meets both conditions, but PPALLL is invalid due to the consecutive Ls. In terms of optimizations, the solution avoids the use of additional arrays or lists to store intermediate results, ensuring space efficiency. The sliding window technique is implemented to run in constant time per character, making the check for consecutive Ls seamless. Overall, this ensures a final complexity of O(n) in time and O(1) in space, making the solution both efficient and practical for large input sizes. This solution solves the problem by evaluating the 2 conditions that determine if a student's attendance record is rewardable. The input string contains only the characters A, L, and P, which represent absent, late, and present respectively. The function checkRecord takes the string S as input and returns a Boolean value indicating whether the student deserves a reward. The following steps explain the implementation. 1. Check for excessive absences. The first condition is to ensure the student has no more than one N in the record. This is achieved using Python's count method on the string. If s.count exceeds 1, the function immediately returns false. 2. Check for prolonged tardiness. The second condition is to ensure there are no 3 consecutive Ls in the string. This is done using the in operator to check if the substring LLL exists in S. If LLL is found, the function returns false. 3. Return true if both conditions are met. If neither condition is violated, the function concludes that the student deserves a reward and returns true. This implementation is efficient, with a time complexity of O(n), where n is the length of the string. The count method and substring search both operate in linear time. The code is concise, readable, and handles all edge cases, such as empty strings or strings with only Ps, correctly. This is the Java implementation of LeetCode problem number 551, Student Attendance Record I. It mirrors the logic of the Python solution, checking if the string contains more than one A or the substring LLL. Key differences include the use of Java's chars method with a filter for counting characters and the contains method for substring checks. The solution is concise and adheres to Java conventions. This problem requires us to evaluate a student's attendance record based on 2 conditions. First, the record should not have more than one A, which represents an absence. Second, the record should not contain 3 consecutive Ls, meaning the student was late 3 times in a row. For example, consider the input string PPALLP. The first step is to check the count of A. Using the count method, we see that A appears only once in this string, so the first condition is satisfied. Next, we check for the presence of LLL by using the LLL in S condition. In this case, LLL is not found in the string, so the second condition is also satisfied. Since both conditions are met, the function returns true for this input. Now, let's analyze the input string PPALLL. First, we count the occurrences of A using s.count. Here, A appears just once, so the first condition is satisfied. Next, we check for 3 consecutive Ls in the string using LLL in S. This time, LLL is present, which means the second condition is violated. Because one of the conditions is not satisfied, the function returns false. Let's look at another example with the input pal. Again, we start by counting the occurrences of A. Using s.count, we find that A appears twice, which violates the first condition. Since the first condition has already failed, there's no need to check for LLL. The function directly returns false for this input as well. To summarize, the function evaluates the input string by checking two conditions: the number of A's and the absence of LLL. It uses the count method to determine how many times it appears in the string, and the in operator to check if LLL exists. If either condition is violated, whether the string has more than one or contains LLL, the function immediately returns false. If both conditions are satisfied, the function returns true. This straightforward approach ensures that the attendance record adheres to the problem's rules efficiently. Here, we analyze the time complexity of the solution by breaking down its key operations. First, when checking if the character appears more than once using s.count, 1, the count method scans through the entire string s to count occurrences of a. In the worst-case scenario, where the string has a length of n, this operation visits each character exactly once, resulting in an O(n) time complexity. Next, for the check LLL in s, the in keyword uses a sliding window approach to search for the substring LLL. This involves comparing LLL against every group of 3 consecutive characters in the string. Similar to the count method, it may need to slide through all n characters, making this operation O(n) as well. Finally, the return statement, which simply outputs a Boolean value, is a constant time operation with a complexity of O(1). Now, combining these individual time complexities, we see that both the count operation and the substring search are O(n), and since they are executed sequentially, the total time complexity becomes O(n) plus O(n) equals O(n). This means the overall time complexity of the solution is O(n). Moving on to space complexity, the algorithm uses a fixed amount of additional memory irrespective of the input size. The input string s is passed directly to the function without being copied, so it doesn't contribute to extra space usage, resulting in a space cost of O(1). For internal operations, neither the count method nor the substring search allocates memory proportional to the input size, they only use a constant amount of space for iterating and comparing. Finally, the output, a single Boolean value, also requires a constant amount of space, making it O(1) as well. Therefore, the total space complexity of the solution is O(1). Let's now consider the best, average, and worst-case scenarios. In the best case, the algorithm terminates early if a violation is found quickly. For instance, if the string is AALLL, the first condition s.count, 1 or the second condition LLL in s would fail after examining only the first few characters. Here, the time complexity would be O(k), where k is the position of the first violation. However, for the average and worst cases, the algorithm needs to process the entire string for both the count operation and the substring search, which results in a time complexity of O(n). Regardless of the case, the asymptotic complexity remains O(n). Let's compare this solution to a brute force approach. In a naive solution, you might manually iterate through the string twice, once to count occurrences of a and again to check for LLL by explicitly examining all substrings of length 3. This would lead to a time complexity of O(n) plus O(n) squared, or O(n) squared, in the worst case. In contrast, the optimized approach leverages the count method and the substring search LLL and s, both of which operate in O(n) time. Additionally, the optimized solution minimizes space usage to O(1) by avoiding additional data structures. This makes the current solution both time efficient and space efficient, providing an optimal balance for this problem. Let's start by addressing some common mistakes students make when solving this problem. First, there's the issue of not accounting for consecutive L's properly. A common mistake is simply checking if LL exists in the string, but this approach won't catch cases where there are more than 2 consecutive L's, like LLL or LLLL. The problem explicitly requires checking for more than 2 consecutive L's, so make sure you're counting all consecutive L's accurately. Next, some solutions misinterpret the criteria for a, allowing more than one in the string. The problem clearly states that a student cannot be rewarded if they are absent more than once, so having more than one should disqualify the record. Lastly, another frequent pitfall is using multiple scans of the string, such as one pass for counting and another for checking L. This is unnecessary and increases time complexity. Instead, a single pass solution can efficiently handle both checks at once, which is a better approach. Now, let's move on to other mistakes that are often seen. One of them is overcomplicating the solution by relying on complex regular expressions. While regex can technically solve the problem, it tends to add unnecessary complexity and makes the code harder to read and debug. A simple loop is not only more intuitive but also more efficient in this case. Another mistake to watch out for is failing to handle edge cases. For example, you should test scenarios like an empty string, a string with no a or l, or even strings with long runs of l, such as LLLLL. Neglecting these edge cases can lead to incorrect results or runtime errors, so it's crucial to account for them in your solution. When preparing for interviews, keep a few insights in mind to approach this problem effectively. First, make sure you fully understand the problem constraints. Critical requirements, like ensuring there is no more than one and no more than two consecutive L's, should be clarified and addressed in your logic. Second, always aim to optimize for simplicity. Interviewers appreciate clean and efficient solutions. For instance, a single-pass approach that uses a loop demonstrates clarity and optimality. Third, show awareness of edge cases. Discuss and test scenarios like an empty string, strings with no a or l, and strings containing long sequences of l. This demonstrates a thorough and critical approach to problem solving. Finally, if you consider alternative approaches, such as using regular expressions, clearly explain their trade-offs. For example, regex might reduce lines of code but sacrifices readability and can be less efficient. Similarly, when considering related problems, like LeetCode number 1221 or number 1047, notice how they also involve string manipulation and pattern recognition, offering opportunities to apply similar strategies. Additionally, other related problems, such as LeetCode number 696, focus on counting specific patterns in a string, while LeetCode number 1404 deals with careful iteration and condition handling, making them great practice for similar logical thinking. When it comes to alternative approaches, one option is a regex-based method. This involves using patterns to identify and count or check for LLL. However, while compact, this approach can be harder to understand and debug, especially for long strings. Another option is the two-pass approach, where the first pass counts and the second checks for LLL. While easier to implement, it is less efficient with its O, N, *O, N operations, so it's not ideal unless constraints are very loose. The best approach is often the single-pass iterative method, which traverses the string once while maintaining counters for and consecutive L's. This method is optimal in terms of time and space complexity, achieving O, N, time and O, 1, space. Although slightly more challenging to implement, it's the most efficient and practical solution for this problem. Great work! We've successfully solved LeetCode problem number 551 by efficiently analyzing the attendance record string. Remember, mastering string manipulation and logical condition checks is essential for tackling problems like these. Thanks for watching, and don't forget to like and subscribe for more coding content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!